Okay, so let's continue with our 12th lecture. So here now we are discussing the induction motor and some basics of that, and we have seen how to get the torque speed characteristic, and in a similar fashion you can also go on and derive the power versus slip characteristic. That is also one useful thing to understand how the power is coming into place, and then where it is maximum. All these things you can derive in a similar fashion. So this parameter alpha you can keep as it is, and using this you can derive all this. So then we have seen how the starting of motor can be done, and the most easiest method but not so useful or not so good method, that is direct online start, that we have seen. And what is the impact of this start method on let's say the current and then power factor, total power, and the torque. So these things we have seen that it's not giving a very good numbers with respect to all these quantities. So very low torque, low power factor operation, current is very high, and complete power is getting dumped in the motor. So this is not a very good option to start the motor. So then we have seen the rotor resistance insertion method. So here we are going for the extreme case where we are inserting whatever is maximum possible resistance and which corresponds to this. So with respect to this point, we are trying to compare the direct online method. So direct online start method. So what we see that if you compute the quantities in similar fashion, the comparatively what we are having is that the torque has improved certainly, which was only 20% of the maximum torque in the direct online. Now we have full torque, maximum torque available. And then current, which was like 5 per unit, now it has come down to 3.5 per unit. And the complete power, which was getting exhausted in the motor, 1 per unit, now it has come down to only 0.25 per unit. So only 25% of the rated power. It is still better compared to direct online, and power factor has also certainly improved. So it's not a big burden on whichever grid system or somewhere you connect this motor. So this method gives some advantage over direct online. And then we have seen another method, which is basically voltage variation. So voltage supply we are reducing, and what we are finding that our torque speed characteristic is basically shifted or shrinked on the along the y-axis. So although we have very poor starting torque, but what we can see that for load torque, something like fan load, this could be a suitable method to start, where the starting current will be a lower value. So that way it will not burden the electrical system wherever this motor is connected. And for a load like fan or blower something, this could be a good option. Slowly we can increase the voltage to the rated value and we can operate at the rated slip. This kind of load profile is okay, but if we have a load profile which is having very high initial torque and maybe a constant type of characteristic, so then this voltage reduction technique may not work. So we need that something like rotor resistance insertion, and which is what is giving us maximum torque benefit. And with that, what we can do, we can start with a high torque value, which is corresponding to the maximum useful resistance inserted in the rotor circuit. And then we can come down to some lower resistance slowly, and finally taking out the complete external resistance. So we will come back to our normal operating point wherever the motor should operate at the low slip value. So different methods have different use and then different advantages. The voltage reduction method you can do on your own and see how the rotor resistance and other things, this input current and other things are getting affected. So that way we can get good understanding. Now we have went on to discuss the another method which is more universal and very useful, because this does not affect the characteristic and its nature. So this is called the V by F method, and basically what we see that the EMF generated by the flux, magnetizing flux, is basically proportional to the frequency and the flux value. So if we simply try to reduce the frequency without changing the voltage at the input, so the flux value may increase and it may saturate the motor core. So which is a harmful thing to do. That is why we try to keep the flux constant and that too at the rated value so that we can utilize the maximum torque benefit of the motor. So which is where we are coming with this kind of relationship where we have the flux which is coming as proportional to E1 by Fs. E1 is the EMF produced by the magnetizing flux across the rotor circuit. So if we are keeping this flux constant, then we have seen that how the torque is affected. So what we find that ultimately if we keep this ratio constant, the torque speed characteristic is not affected at all. Whatever Kt constant was available earlier with the original E1 and omega s, that means the rated values, that same thing is followed even for a very low value of frequency and voltage. So this is a very advantageous method where we are not shifting or shrinking the torque speed characteristic and we are not unnecessarily burning the power in some resistance or somewhere, and still we are able to achieve good starting torque if you see from the rotational speed point of view. So this is the torque speed characteristic corresponding to the rated value. And if you keep on changing the rated frequency while maintaining this E by F constant, this is basically you are shifting this while maintaining the shape as it is. So basically these are all different synchronous frequencies where the motor is operating. And slowly you can reach to a point where your actual frequency may be a very small. No, the slip frequency may be a very small number, which is actually your operating frequency itself in terms of the actual physical frequency, physical rotational speed. And then slowly we can go on increasing the speed or our synchronous frequency, and we can come back to the actual operating point wherever we want. Actually, we can operate anywhere. There is no problem. The same motor can be operated with any frequency up to the rated frequency, even beyond that, but then certain things change. Understanding my point? Now, this method is useful for both wound rotor induction motor and squirrel cage induction motor, and this does not need any external resistance or any degradation in the characteristic. So all these things are intact. The starting torque is intact, the maximum torque is intact. So these things are good. Now, the problem here is that when we are talking about E by F constant, so just I'll draw the equivalent circuit to give you a feeling about what E1 is. So when I am talking about this, I am saying from the point of view of actual circuit or actual equivalent circuit of the induction motor. So this voltage, what is coming across this magnetizing inductance, this I am calling as E1, whereas our supply voltage is here. So certainly we cannot measure this voltage, what is coming across the magnetizing inductance. So what we do that we say, yes, the supply voltage is approximately equal to the air gap or this EMF what is generated across the magnetizing inductance. And this kind of approximation we take, and then we ensure that instead of E1 by F equal to constant, we can maintain Vs by omega s or F as a constant value. This is more practical because this can be measured, and we are giving this from external source where we have this kind of facility to vary this voltage. So then this is a more practical approach than this cannot be measured. So kind of fictitious, we have only theoretical value of this. Now this approximation we were discussing, till what point this is valid. Let us say when we say that V1 is approximately equal to E1. So what basically the relation between Vs and E1 is that Vs is basically this. Now what happens, as long as this drop, the stator drop, is negligible compared to E1, you can say that Vs is very close to E1. As long as this drop what is coming across the resistance and the leakage inductance. So this is true whenever you talk about any frequency which is greater than say 10% of the rated frequency, this approximation is valid. What happens if we go below 10% or 5% of the rated speed? This value may not be dominant because XLS is something which involves frequency as well, omega LLS. So with reduction in frequency, this is also reducing. So this does not affect our computation much. But the resistance, what is there, it is a kind of constant value. This is not affected by frequency. So this remains as it is. And particularly when we are drawing almost rated current near the starting of the motor, then this drop is very, very dominant compared to the other two terms. So what may look like if you have the phasor, let us say this small could be the E1, and then because this I is still rated, so IR could be very dominant, and then you may have. So this could be the difference, something like what I have drawn here between Vs and E1. And this is for any frequency, let us say if less than say 5% of the rated value. And particularly for low power motors, where the rotor resistance is significant. For high power motors, we have a small value of resistance. So this approximation may be valid even for very small frequency as well. But for low power motors particularly, this approximation doesn't hold good. Now, this is not true. We have a lot of resistance drop coming over there. Understanding my point? Now, if this is not true, then what to do? So we need to compensate for this additional resistance drop. So if we are able to compensate, let us say this ISRS plus J IS XLS plus E1. E1 is the quantity which we are trying to maintain fixed with respect to the ratio of E1 and omegas we are trying to maintain fixed. But when we are going below this kind of frequency, this becomes dominant. So we need to compensate this value on the supply side so that this ratio is maintained. This E1 by omega S ratio is maintained even for low value of frequency. So when you draw the V by F profile for induction motor, say this is my rated frequency, this is my frequency axis, and this is where the rated value is. This is 1 per unit, and this is my voltage limit 1 per unit. So what I'm trying to do, that I'm trying to move somewhere on this line where the V by F ratio is maintained constant. And at the rated value, V by F constant is one thing, but V by F maintained as a rated value of whatever rated value is there, then that will ensure rated flux. If you keep V by F some value constant, but it is not at rated, it is lower than this, then it is not rated flux. You understand my point? So computation you can do if the motor voltage is say 400 volt line to line, then your RMS voltage will be something like this by root 3 simply. So this is your voltage, and then you have to check with this. This should be the rated ratio what you have to maintain, not any random value. That's why when I draw 1 per unit, this is also reaching its rated value. This is also reaching its rated value. So this is how this should look like. Now what happens when we move beyond the rated frequency? We have already touched the rated voltage. So because of machine insulation issues and all, we cannot generally cross this limit of voltage. So what we do after this, we do not increase the voltage, but we can increase the frequency without any trouble. So beyond this point, beyond this rated values, this characteristic becomes flat. So if I draw with a red line, something goes like this. This I'm talking about V by F profile, how your voltage is rising with respect to frequency. For very low value, what I was telling earlier, that up to say 5% of the rated value of frequency, we keep the voltage constant. We keep this at 0.05 per unit, up to this 0.05 per unit of frequency. So the red line is actually what we follow for V by F profile. This is the initial voltage boost what I was talking about, which will compensate for the resistance drop which was unintentional at lower frequencies. For higher frequencies, this is fine. So Manvendra, again you are missing from the camera. What's the issue? Where are you? Why are you switching off your camera again?
Actually, sir, data consumption is fast whenever I open my video, sir.
You ensure good internet connectivity and everything, right? You have to attend the classes.
No, sir. Internet connectivity is good, sir, but sir, data consumption, sir, maybe
So
sir,
you
data
take
is
such
limited.
schemes, no? Take such package where you have enough data.
Okay, sir.
You cannot remain invisible throughout the semester, right?
Sorry, sir.
Okay, so this is what we are getting. Now, if you see about the flux, what is happening with that? So blue line, if I draw, up to the rated frequency and rated voltage, the flux value is maintained at the rated value. And then what happens? Once you cross this point where the voltage has reached its limit and still you are increasing the frequency, actually the flux drops as inversely proportional to the frequency. So this is the zone which we say that is constant flux or constant torque zone. Here we can maintain rated torque. So I told all the characteristics which are moving something like this and then again like this. All these characteristics fall inside this. But as you go on increasing the frequency further, there is a reduction in the torque value. So the characteristic will start dropping. Are you able to visualize that? So after here, there will be reduction in what you can achieve as the maximum torque after this rated value. So this is why this zone is called constant flux or constant torque. Now here what we have is known as the field weakening zone. So here we have reduced or degraded our flux value. We cannot do anything but to degrade it because voltage has reached its limit, but still we can operate. So this is going beyond the rated value of your frequency of operation. You understand this point clearly? So torque, as I said, it will be maintained constant up to this point and then it will degrade similar to how flux is degrading because it is directly proportional. Fine?
Yes, sir.
Also, this field weakening zone may also be called as constant power zone because as our torque is reducing, the speed is going increasing. So the product, the power remains constant. That's the rated power. You cannot take anything beyond that. So power will have some characteristic like what we are having as V by F profile. Power will be increasing up to this rated value and then it will become flat. So different profiles, no, whatever we have, power, then torque, flux, V by F, all these characteristics you should be able to draw based on these computations what we are having. Understand my point?
Yes, sir.
So V by F concept is clear to all of you. Why do we go how do we go and what we do there?
Yes, sir, clear.
Good. So any doubts, any confusion you have, you may ask, because after this we will move to realization of power converters. Okay. So now here, when we are talking about this kind of working profile for the motor and other things, what we basically need is that our voltage is changing and frequency is also changing continuously. So power supply or some arrangement where we should be able to generate variable voltage, variable frequency. This kind of arrangement is needed. Understand the point? So now how is this possible? What can be done? So either you have a source like that which can be controlled in this manner. You have a source which can be controlled, that you give an input for voltage and maybe an input for frequency, and it generates the output, which is exactly tracking this. This is the ideal situation. Correct? So when either you have this kind of arrangement, or if you don't have, what you can do, you can again have a power converter which can generate the voltage output at this requirement, certain voltage and frequency. And of course, it may have some input, maybe a voltage source or a current source or anything, AC, DC, whatever. So this is where, when we are trying to have the utilization of induction motor better, when we are trying to have better operation of induction motor, we need the power converter to make it feasible, to make it practical. So then, first very popular and very simple thing to do is that you have DC input voltage. Somehow you maintain a DC input voltage, and then in between you have something called as DC to AC power converter, and it will generate the three-phase balanced output power based on what is your requirement. If you want to maintain V by F and then you give the command for frequency, so it will generate voltage and frequency like that. You understand my point? Now this is what we are trying to do. We are trying to realize this converter, DC to AC converter. This you can also call as inverter. And particularly because we are dealing with three-phase, so we will see how three-phase inverter is realized. Understand my point?
Yes, sir.
Now,
Yes, sir.
let us just recap a little bit how and what we have done in case of DC-DC converter. So what was the arrangement for DC-DC converter? When we were trying to generate any DC voltage, what did we do? Yes, someone? Things done in DC-DC converter are basically extended for DC to AC converter. So what was done over there?
Sir, in DC,
Yes, one by one, tell.
sir, in DC to DC converter, firstly, we realize how to transmit power from. We have to focus that we transmit power from voltage source to current source,
Okay.
and then after this, we realize the importance of inductance, capacitance, and then finally we realizes the switches on the basis of VI characteristics.
Yeah, but what is the bottom line of this, all this thing?
So, input power equal to output power.
Yeah, it is fine. Let's say you have DC input. The most important component for power conversion is this SPDT switch. If you don't have this, then any of these power conversion methods what we are talking is not possible. You understand my point? Now what this single pole double throw switch is doing, what it is doing.
Giving the input for some time and then stopping for.
So basically it is connecting to either throw T1 or to throw T2. And in effect what we are seeing that at the pole voltage we have a voltage profile like this. You understand my point? Just because we are able to generate this different width or no for the pulse what is coming on the output, we do have arrangements to make it smooth, and effectively we can generate average voltage which can be somewhere between Vg and 0. This point is clear?
Yes, sir.
Yes, sir.
So this is the most important part in our power converter. Now the same arrangement will be used for realizing the DC to AC power conversion. What do I mean by DC to AC? See, earlier you had input like this and you are generating output like this. DC input is there and you are generating a pulsed DC. Now what we want to generate something like which is changing its polarity also. Understand the point? Now, how can we do that? How can we change the polarity?
By having bidirectional voltage and bidirectional current switch configuration.
No, where did I say about direction? Did I mention about power flow direction? Bidirectional generally refers to direction of power flow. Are we talking about power flow from the
No, sir.
load to source?
No, sir. Because here power flow will be always like in this case from DC to AC side, considering simple motor operation. But problem is because of inductive nature, the current sometimes will be lagging. So during that time, we need both directions of current also, sir.
The bidirectional of current saying is okay, but don't say bidirectional power as of now. What?
Sir,
Bidirectional voltage and current, sir,
sir,
not power.
sir,
Yes, sir.
sir, in DC to DC, we are getting voltage during on time, but during off time we are actually short, actually creating a voltage zero. Now, if we develop a voltage that is negative on that period, then we can achieve this.
Perfectly. This is what we have to achieve. See, what we are doing earlier, we are having only one polarity of voltage, and other side we are shorting it to 0 here. Now we need arrangement where we are able to generate both polarities of voltage. So we need certainly two SPDT switch. How this is going to help? Let us see. You have the voltage source and say this is the load which you are trying to connect. Now if you have SPDT switch connected at both ends of the load, so let's say this is A and this is B, and correspondingly this is A1, A2 and B1, B2. Now you have created the option that if you connect A and A1 and B and B2, what will be the output? So VAB I can write.
VG.
It's VG. If you connect AA2 and BB1, what will be the output?
Minus VG.
Minus VG.
Minus VG. Are you getting this point? We have only made arrangement so that we can apply a reverse polarity of voltage across this load. Nothing more. And which is achieved through two SPDT switches connected here, connected across the load. And this forms the basis of conversion of voltage from DC to AC. Now you have this different polarity over here in the output, and as long as you maintain VAB average equal to 0, which means what? You are alternatively generating positive and negative cycles of the voltage. This is a simplest manner. This is in the simplest manner you can generate the AC voltage. It's not sinusoidal. Quality may be poor, but at least you have generated. We can improve the quality, but at least when we are able to generate something, the quality comes after that. You understand this point?
Yes, sir.
Yes, sir.
Deepak?
Yes, sir.
Now, here we have actually four options. No, two options we have discussed. But because each is having each pole is having two options, so actually we may have two more arrangements. Let us say when A is connected to A1 and B is connected to B1, what will be the output voltage?
The 0.
0, because both are shorted to the positive of the input voltage. And when you have A2 and B2, what would you generate? 0 again. So whenever you are generating or applying some voltage across the load, there is power transfer, say either connection like this or connection like this. And whenever you are shorting the load, Deepak, can you mute? And whenever you are shorting both the terminals to the positive, you have the current circulating within the load. Or if you connect to the negative, then also you have current circulating within the load. So zero power transfer during these two states. So four states are possible over here for this double SPDT switch arrangement. You understand my point? So actually what we were generating, the VAB can be slightly better. It can be generated like this as well. Say this is 2 pi, this is pi. So we may have 0 level also generated. Correct? So we will discuss about waveform quality and other things, but this is the possibility what we have when we are talking about single phase VSI or voltage source inverter, because we have voltage source as input. So this is called voltage source inverter or converter, whatever you want to call. And because we have only single phase load, so this is single phase VSI. Clear? Now, how many SPDT switch we need for three phase VSI?
6.
Okay, what if I say 3?
Yes, sir. 3 is sufficient.
3, 4.
So now instead of going by 6 SPDT switch and all that, what we do basically in case of 3-phase system, we realize the output on per phase basis. So what is meaning of per phase basis is that you create a fictitious point at the input. Say this is 0 and the total voltage is say VDC. So with respect to this point O, the positive DC bus is say plus VDC by 2 and negative DC bus is something like minus VDC by 2. Now this is happening with respect to the voltage O, correct? The point O. This is called DC bus midpoint. Now if you have SPDT switch here, and the pole is connecting the load terminal. So I have denoted it with R. Now the voltage VRO, that means the voltage at point R with respect to point O, has two possibilities. It can be VDC by 2 or it can be minus VDC by 2. So say this is R1, R2. So when R is connected to R1 and when R is connected to R2. You understand my point?
Yes, sir.
Many a time this may not be a physical point. This is just a fictitious point. But if you are able to generate this kind of voltage here at R, then the other phase will also create similar, where this point will cancel out and ultimately you will have balanced three phase. So if I talk about Vry voltage, for example, what is this basically? VRO minus VYO, isn't it? And if you take VR as a separate voltage point and then VO as a separate voltage point, then ultimately you have this, which means the actual terminal voltage coming over there. Now this fictitious point is balanced. So in the line-to-line voltage, this whatever fictitious point we are creating is kind of cancelled out. So with the 3 SPDT switch, one for each phase, we can have the realization of 3-phase voltage source inverter. So I will draw the circuit over here. Is this point clear to all of you, or there is some confusion? Yes, anyone?
Hello, sir. Can you repeat the VR word?
Okay, the better way to do is see it through the waveform. When we say that we are generating balanced three-phase voltage, the VRO, VYO, VBO are balanced, even if O is fictitious. I am not claiming that it is the actual physical point, right? This point is clear, right? What I am saying?
Yes, sir.
Yes, sir.
Whenever there is confusion, ask. Otherwise, what will happen? Your confusions will pile up. Say this is R generated by, RO is generated by this R phase terminal and with respect to the DC bus midpoint and so on. Now YO is basically 120 degrees shifted, so it will come or start somewhere from here. And then BO will be something like 240 degree lagging. See this point? Each level is VDC by 2 minus VDC by 2. Simple operation I am having. So now, if you take out the line-to-line voltage, what will happen? You are doing VRY as VRO minus VYO. So what will happen? We are concerned about R and Y. So we will mark all the transition points for R and Y. Now, tell me, up to this point, when R is positive and Y is negative, what is the value of VRY?
VDC.
So VDC.
sir.
VDC. During this point, when both are positive, it will be 0. Then again, the next interval where this is negative, this is positive for another 120 degree. So this will be what? Negative minus VDC. Again, both are coming negative, so this will come here, and then this cycle will repeat. Similarly, if you draw VYB or VBR, that will be only shifted form of this waveform. So now, are you able to generate AC voltage at the load terminal? Yes or no?
Yes, sir.
Yes, sir.
Yes.
There is no fictitious point in this. These are both load terminals, R and Y. Similarly, YB, BR, all these will be load terminals. So using this kind of arrangement, what I have here, 3 SPDT switch, I am able to realize 3-phase voltage source converter. Similarly, if you have 5-phase, 9-phase, all these converters, you can again have multiple SPDT switches and you can realize any voltage source converter. Am I clear? Now, important point to note over here is when we have single pole double throw switch everywhere, we have only 2 possibilities for the output. Is there any third possibility for this? I am talking particularly for 3-phase converter, not single phase. Is there any third possibility for this voltage, pole voltage? This, by the way, VRO is popularly called as pole voltage. Okay, so the different terminologies we will have for our correct understanding. So anything what you generate with respect to this, let's say midpoint, and then this pole, this is called RYB. So simply this is pole voltage. Okay. Yes or no? Quickly.
Yes,
Yes, sir.
Yes.
Any confusion in this?
sir.
No, sir.
Good. So is there any third possibility for the output voltage here?
No, sir.
No,
No,
sir.
sir.
Then that is why this is called 2-level VSI. You cannot generate any other voltage level. Understand the point? Now, if we have to go for, let us say, introducing one more voltage level for the voltage source converter, what do we need?
One more level. We need to have one more point so that
One
we can
more
get another
set
level.
of switches.
Sir.
This is correct. We need one more point for connection of the pole. So what we had as SPDT, double single pole double throw, now it becomes single pole triple throw for the 3-level. So now we have 3 options for this pole R, R1, R2 and R3. Now this DC bus midpoint is a physical point which is having connection between the pole and this point. So with respect to this point, your positive voltage is plus VDC by 2 and minus VDC by 2. So based on where you are connecting your R, you have 3 possibilities: plus VDC by 2, 0, minus VDC by 2. So here R is connected to R1, R is connected to R2, R is connected to R3. Any doubt in that?
So here we need 2 sources, right?
What?
So do we need 2 sources here?
You need a midpoint. You can use that capacitor in series to realize that with one single source.
So then the polarity of both the capacitors will be same, and the voltage apply across those capacitor will be in the same direction. So
Yeah, it
O
is in the
point.
same direction.
So the O
What's
point will be plus VDC, not the 0, I suppose.
This point.
Yes, sir.
You missed the first line itself. When I say this is the reference, only with respect to this, I am saying this is plus VDC by 2, this is minus VDC by 2. Then what is voltage at this point?
Yeah, in that respect, because the source itself is actually plus VDC on the upward side, right? If we talking about in the practical term, right? So that
See, everything
bottom
what I
line.
talk here is practical. I am not talking about anything which is not practically possible.
I mean, sir,
Okay, now
yeah.
tell me, what is the voltage at this midpoint O?
Currently, that's my confusion, sir. I don't know how the minus VDC by 2 we get here.
How you get? See, voltage is not any absolute quantity. We only talk about voltage with respect to some reference point.
Yes, sir.
Always.
Yes,
If
sir.
you don't have any reference point, voltage doesn't have any meaning.
Yes, sir.
If I am saying that this is VDC, this voltage is VDC, this is with
Yes.
respect to what?
So ground.
Where is ground?
I mean, with respect to 0
With
point.
respect to the negative point.
With respect to, okay.
If with respect to negative point, I am saying this is plus VDC, then with respect to midpoint, can I not say that this is plus VDC by 2 and this is minus VDC by 2? Yes, Ajay.
I'm a bit confused. I will look into it.
Because you are confused with voltage, how you measure.
Yes, sir.
Can you measure the absolute voltage of any point?
So voltage is always a voltage difference.
Voltage is always voltage difference.
Yes, sir.
How will you measure voltage difference? Always
Well,
when you have 2 points.
yes.
You are saying this voltage is VDC because you are measuring between these 2 points.
Yes.
If you connect the multimeter with negative terminal here and positive terminal here, what voltage the multimeter will show?
So it's minus VDC.
But your voltage is positive here.
Yes.
Then how is it showing negative?
So we have changed the polarity. We have changed the respect. We have.
You have changed your reference point.
Yes.
What is meaning of polarity? You have changed your reference point. Earlier your reference point was here, so you were saying this is at plus VDC. Now your reference point has shifted here, so you are saying this is minus VDC. The meaning is same. Potential difference between these 2 points is VDC. That is all.
Yes, sir.
Even if you connect 2 sources, let us say I connect 2 sources. One is VDC by 2, another is VDC by 2, like this. Can you say this point is 0 in absolute sense?
No, sir.
You are saying this is 0 only with respect to this and this. When you say this is 0, then this is becoming plus VDC by 2. When you say this is 0, then this is becoming minus VDC by 2. See that you have connected the positive of this and negative of this together.
Yes.
Your reference point for both measurements are one place it is negative terminal, another place it is positive terminal.
Yeah, right.
So it's only potential difference what we talk about. We can never have any absolute potential value. Is this point clear to all of you? Quickly, yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Now,
Yes, sir.
using this SPTT switch, the single pole triple throw switch, we are realizing this kind of voltage output. So how this may look like, again, because we have 0 voltage. So now the pole voltage may look like this. See, this is 2 pi. Am I clear?
Yes, sir.
So similar to that previous 3-phase 2-level case, you can extend the branches of this or legs of this converter also, and you can realize a multi-phase converter as well. Fine. Sukumar,
Yes, sir.
Shambhunath, Anirban,
Yes, sir.
clear?
Yes, sir.
Uday?
Yes.
Yes, sir.
Yeah, Neelam, Drashti,
Yes, sir.
Manvendra,
Yes, sir.
Sampan, Ashish, both Ashish.
Yes, sir.
Yes, sir.
Good. This is the basis of our realization when we are doing for voltage source converter. Now, because time is over, so tomorrow some portion I will take to have the realization of current source inverter. And then what switches we can place at all these places. It is still only generic SPDT, SPTT switches, all that we are discussing, but how to connect the actual devices, this we will discuss. So, and then we will complete the realization and move towards the other sections of the course. Okay, tomorrow we will have discussion on, okay, before closing this, any doubts again up to this point?